Okay, yes. Question? Go ahead. What? In the lab you have what?
We have francium in the labs.
Francium? What's that?
Aluminum,
yes.
No, because we want to put some in water.
You cannot. You cannot do any dangerous things, quote unquote dangerous things in the lab. So, anyone have any questions about the grouping of experiment session? I got a lot of questions about whether you can group with another session. The answer is unfortunately no, because we grade only within one session. The grade consists of like a portion, 10% for the experimental part, and that part will be graded only in this session together with your other grades to calculate your final grades. The only thing we merged is the final exam. Other things will be relatively independent. That's why. So actually, if you want to group with another session, you can either go to that session, you can still change your enrollment. So the enrollment will, I think the enrollment will be closed by the end of this week, right? So you still have chance to like swap. Because I know this session, I have like almost the maximum capacity, over 60 already. So if you want to enroll in another session, I actually recommend you to do that because the other session only have like 40 enrollment, over 40 enrollment. Yeah. So, for those who come late, you feel free to grab the chocolate and the periodic table. So, if no questions, I think the first experimental session will follow after the add and drop period. That means maybe next week, Wednesday, will be the first lab session. I think our TA will give you some instruction about that. Or they have some plan maybe to postpone it by 1 week because we have like around 60. So that means we will have like 13 to 14 or 15 groups. So each week we will accommodate 2 groups. That means in total we have like 7 to 8 weeks to finish all experimental session. As you can see that this semester we have like 13, 14 weeks. So we still have some freedom that if you cannot come on that specific day, you can do some swap. But you have to tell TA at least 1 week before so that they can prepare, like make some alternations. Okay? So for those who come late, you can grab a periodic table and also a chocolate coin. Good luck, chocolate coin. Okay, so do you still remember what we had last time? Actually, from this lecture, I think we formally entered the world of material science and engineering. So as I said before, it's more like chemistry, high school chemistry kind of review, right? So not sure if my voice is like recorded, because room PC, notebook, I don't know. Okay, because I got some technical issue about the sound. That's why I didn't post the recordings for the second lecture, because second lecture we lose the sound. Okay, I hope this time we got it. So last time we discussed the electron configuration, right? For the electron configuration, important thing is that you understand the concept of what is the ground state and what the valence electron, how do you count valence electron, and what is the stable state. I believe Pauling exclusion rule had already been explained in your high school. So here as a review, I think when you review the course content, the important part here would be how do you distinguish? How do you distinguish the concept of ground state, stable state, and also how do you calculate the valence electrons? The valence electron corresponds to the outermost shell. And this shell, note that this shell is the principal shell, it's not the subshell. So that means here, if you count the valence electron for sodium, you have to count 3s shell. So that is 1. But if you want to count the valence electron for sulfur, you have to count 3s and 3p altogether. Okay, so for stable electron configuration, only for if you have the periodic table, only for the last inner gas, they have the atomic structure corresponding to stable electronic structure already. Otherwise, for other periodic table elements, they do not have the stable electron configuration yet. But they can form the stable electron configuration by receiving or giving the electrons of the outermost shell. Okay, and ground state. Ground state corresponds to the lowest possible energies of the electrons, all electrons that can be filled into the electron orbitals. So last time we used 4 important quantum mechanical numbers. Do you remember? We have the principal number, we have this suborbital number, and we have like magnetic number and the spin number, right? This number tells you the main energy state. And this number tells you, like, if you have the main energy state, and this tells you the sub-shell energy state. So the energy of S will less than the energy of P, will less than the energy of D, will less than the energy of F. We call it sharp, principal, diffuse, and I forgot. And they have the ability to host a certain number of electrons depends on the Pauli exclusion rule. And this too doesn't really relate to the specific values of the energy of electrons to try to fill in, but they will affect the electromagnetic properties of the material that's like more advanced kind of property. So this one corresponds to, like, for example, this one n equals to 2, then L can be S and P. And for S, it has like ML is like, I think 0, right? And for P is like, what was that? -1, 0, and 1. So that's for ML. And for MS, for each of the specific route, it has like positive, negative, 1/2. So last time I give you an analogy, like your undergraduate hall, you have the main floor. In the main floor, you have like 1 bedroom, 2 bedrooms, 3 bedroom, 4 bedroom, and in each of the bedroom, and you can choose like bundled together, like up and down, right? So those correspond to the 4 quantum mechanics numbers that tells you the energy levels, how a electron try to occupy certain orbital. And that closely relates to how to arrange the electrons into a ground state for a specific atom. Because we know from the atomic number that equals to the electron number at the neutral state. So if you have the total electron number at hand and then you want to fill them one by one, you have to fill from the lowest possible energy state and then to the second level, so that if you fill in all the number of electrons for specific element, you achieve the lowest possible energies, and that corresponds to the ground state. but that one may not correspond to the stable state because the stable state corresponds to the fully filled outermost shell. So not necessarily always fully filled outermost shell. Okay, so that's the content from last time. And this time we will discuss periodic table. Okay, so let's see if I can show you the periodic table. And this part, I believe maybe some part in mainland or in some like other nations you already learned, right? So this is also some kind of review. Let me see if I can use this one. Okay, so that is the same as the periodic table you have. Maybe I can make it smaller. Okay, of course, the first one we introduce here is called inner gas. So each of the elements here correspond to an electronic stable configuration. So in the quiz, I will ask you which from the below choices always give you electronically stable configuration as an atom. So the answer is inert gas. So you have to be very clear what that is, right? So the quiz is open book, so you don't need to worry. Okay, and here, this periodic table has some color map, right? So this kind of color map tells you what is the metallic, what is the non-metallic. So here is all non-metallic. Non-metallic actually is a small amount, occupy only small amount on periodic table, include hydrogen. Hydrogen also in the same color. Okay, so for each of the element here tells you how do you interpret the number. So here correspond to atomic number. For example, if I ask you what is atomic number, A, proton number, B, electron number, C, neutron number. So you need to choose the proton number because neutron number and electron number subject to change. So this one always correspond to the proton number, and that can uniquely tell you what this specific element is, right? And this is the chemical symbol that you know. And here you can see the atomic weight. So this is atomic weight, not the mass. So that means this is the weighted average of that specific element widely available in nature, maybe on Earth, right? Okay, so that's the English name of it. And also here, this number tells you the main electron orbital. For example, let's see if I have other, where is this one? We are familiar with sodium, probably a little bit reflective. This is like, for example, this one, 2A2. That means outermost shell has how many valence electrons? 2, okay, 2. And this one, outermost electron has 1, right? And look at this one. So for this one, outermost shell has 6. That means it has 6 valence electrons. Okay, so maybe other things you're very familiar with, but maybe this one is not so familiar. So this corresponds to the shell, the electrons that occupy in the shell. But it doesn't really give you like S, P, D, F, such things. But this is just a shorthand expression that you need to know. And here for chloride and fluoride, so it has like 7. Okay, so for transition metal, actually those things is not quite standard. Actually, as I said, it has like partial filled d orbital in the upper main energetic level. So those type of things is just the way they present the electron configuration doesn't mean like really it's like one electron participate or two electron participate. So you cannot simply just use this kind of electron configuration to judge their behaviors in chemical reaction for transition metal. So at this stage, you just need to at this stage, I think you just need to be clear that transition metal cannot be fully governed by Pauling exclusion rule, but the main groups, like A groups, they can roughly judged by the things that we learned. Okay, so here is the similar periodic table, but I didn't print this one because it doesn't show the electron configuration, which is also very important when the element participate in bonding, and that's gonna be the most important thing in this chapter, and it will be examined in both quiz and midterm. So, okay, so there's this kind of staircase, as you can see. Also, that marked as this yellow staircase here. That's the semiconductor. So that means this is like transition zoom. This is a transition zoom from the metallic element to non-metallic element. So in this metallic element zoom, there's one exception, is hydrogen. Okay. And there's like some very complicated element, like the rare earth and actinide. So for rare earths, actually they all correspond to the permanent magnets materials. Okay, so that's for like electric motor. So if we want to have like the electricity, we need to have like the electric motor that can have like the electricity induction, so forth and so on. The rare earth element somehow correspond to that kind of applications. But the electron configuration for them is like very, very complicated, cannot be simply explained by the knowledge that we covered in this course. Okay. Okay, so some important terminology also probably will be examined in the quiz. Like here, I said this is the inner gas, and here is the halogen. Why is it called halogen? Because people use it as a gas to light up our light bulb. Okay, so we call this like halogen light bulb. Okay, so they all have like 7 outmost share electrons, valence electrons. Very easy to receive one, to exhibit -1 charges, ions. We call it anions, right? And become the stable state. And here is the active metal column. We call it alkaline metal for the first column, except the hydrogen, lithium, sodium, potassium, I don't know how to pronounce, okay, cesium. Okay, so those type of materials are extremely active, okay, so usually used in the battery, okay, like lithium battery. Nowadays, people explore sodium battery, not potassium. So as the atomic number increasing, the chemical activity get like more and more active, okay? So lithium is used very like common in battery materials. And for the second one, we call it alkaline earth materials. It has 2 valence electrons in the outmost shell. They are also active, but not as active as the first column. And like magnesium, calcium, they are popular material to form compound. What kind of compound? Oxide compound. They are very, very popular to form compound together with oxygen or nitride or like phosphorus or sulfur to form that kind of stable compound. That kind of stable compound is a very important engineering ceramics, like used in the high temperature furnace to heat up things. So usually if you use metals, it has the resistance, right? And then if you apply electricity, it will heat things up. That's like the regular electric stove that you probably use at home. But engineering-wise, if you want to achieve like 800 degrees Celsius or 1,000 degrees Celsius or even higher, then you need to have a more stable and durable materials like ceramics. And it can hold very high temperature without melting. So for that, the aqueous metals are easy to bond with the oxygen or nitride or even like carbon to form the carbides or oxides or nitrides. Those type of ceramic material, ceramic compound, they have very, very high melting point. So application for them is try to use as the heating or heater rod put into high temperature furnace. Okay, so most single substance metals that used in engineering all come from actually the transition zone, the transition metallic material zone. So like iron, like cobalt, like nickel, they are magnetic, and at the same time they can be used like as a stainless steel to build the buildings or bridges or like transportation vehicles, right? And we also have like novel material, like very expensive material, begin with silver. This is expensive, but compared to other more expensive metals, this is like least expensive one, right? So used in jewelries, like gold, like platinum, and also this one, PD. This is platinum, this is platinum, and this is the rhodium. Rhodium, those type of things, sometimes, you know, like in very expensive jewelry brand, they have gold as a majority of those like rings or necklace. But if they want to use the machine to like make a very beautiful sculpture or shape or very complicated but very small shape, they need the material has certain hardness, right? So if they use like 90%, 999 gold, it's expensive, but it's soft. So it's very hard to machine, to fabricate those very beautiful designs. Then what do? They add this even more expensive content from here, okay? So they have like relatively high hardness. So if they add like 1% or even less than 1% of this element into gold, that can tremendously increase the hardness of the gold, so that they can use like the polish machine, use other kinds of like the milling machine to create very fine structures that they want. Otherwise, they cannot. So many jewelries that you see from those like Tiffany or Cartier, they all use this kind of technology to add put element together to form alloy. Okay, that can improve the mechanical property, and those type of things we are going to learn maybe in the next few chapters. Okay, so actually the metallic material are all from here, right? So those are the things you need to be aware of from the periodic table. And here I said this is semiconductors. Okay, so in this chapter we are going to discuss bonding. So one important